Since sunspots matter in terms of what happens to the solar activity, we want to be able to count the sunspots. We want to make sure that the way we count them today matches the way they were counted in the past. This is one of the issues that sometimes happens, in a lot of the sciences, is that you measure something one way and then you find a better way of measuring it, but then your new measurements don't really match the old measurements. Okay, now we actually realize today that sunspots are maybe not the best way of counting sunspots, might not be the best way of measuring solar activity, but this is how it's been done since, we've had telescopes to look at the sun. So that makes it a way of correlating today's activity to the past activity. So the way that we do this is we define something called the Zurich sunspot number. The Zurich sunspot number has several different aspects to it. It has what we call a relative sunspot number and an observer factor. The relative sunspot number we get by taking the number of spots and adding that to the number of groups of spots. So in this image up here, I look at that and I see a group of spots right there. I see a group of spots right there. I see a group of spots right there, and I see a group of spots right there. So the groups of spots, that would be 4 groups of spots. And in that group of spots, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I see 19 individual sunspots. And so I would say that the relative sunspot number is going to be 10 times 4, that's 40, plus 19, so the sunspot number is 59. Okay, that doesn't not mean there's 59 spots. That means that's a way of categorizing a number based on the spots. The reason we do this is we realize that where the groups of spots are, that's really a region of activity. That's where all the stuff that's making the sun do what it does happens. So the number of groups is more important than the number of spots. The number of spots is related to how active the groups are. Now, the thing is that a different observer might see things differently. You get a bigger telescope, you might see more things. Smaller telescope, less things. And so the observer factor takes that into account. So the observer factor would allow you, if every time you look at the sun, you get half of the official number, then this turns out to be pretty reliable. Using you with your experience and your telescope, you see half the official number. So if you measure a number, multiply by 2, and that's a pretty good match for the actual number. Likewise, if you're super experienced and you have a super powerful telescope and you see 4 times the actual number, then whatever you get, divide by 4. So multiply by 0.25. So that observer number turns out to be a very reliable sort of metric there. And so using that, we can get a number that we can then compare to previous decades and previous centuries of observation of the sun to figure out really what's the sun doing. The 23rd cycle, this is actually when I was starting to get seriously into monitoring solar activity. And so these are like weekly averages of sunspot numbers. And in the middle is this smooth sort of thing. So it peaked up here. Actually, it had peaked, dropped, and peaked again. So it had a double peak up there. Some sunspot groups do that, some don't. Turns out when they double peak like that, it makes it a more active cycle. We'll talk about that activity later. Okay. Sunspot numbers are a little bit hard to measure because they're observer dependent. But you can also use radio flux. 10.7 centimeter wavelength radio waves can be used to pick up the sun. And here I have a graphic on the left measures the radio flux over the 24 cycle, and on the right is the sunspot numbers over the 24 cycle. And you notice that these two graphs are very, very similar to each other. So that means radio flux, which is a much more objective measure, can be used to measure solar activity. So what you would do is use the radio flux and use a little formula that tells you the effective sunspot number. So that's one thing you can do, is use the radio. Okay. Well, how's the solar cycle progressing? Okay, so we're watching this, and we notice that, the 19th cycle, this was a very active cycle in there. The 20th cycle, less so. And then we went back to big cycles, the 21st cycle, 22nd cycle, 23rd cycle. And then what happened was, at the end of the 23rd cycle, we had one of the longest and least active solar minimums that we had had in over a century. And then the 24th cycle here has turned out to be puny. Okay, 24th cycle has ended with another extremely long and depressed minimum. Very little activity going on. And then that's leading into the 25th cycle. We've seen a few sunspots from the 25th cycle start to appear, but not very many of them. Okay. So, based on what we've seen, we can project what the 25th cycle might look like. And we're expecting the 25th cycle to be basically about the same size and duration as the 24th cycle. So another miniature wimpy cycle right here. Okay. International sunspot numbers, the numbers I was just showing you were kept from were kept by NOAA's Space Weather Prediction Center in the United States. This is actually from the Royal Observatory of Belgium right here, and it's following the 23rd cycle, and then down here at the bottom here, they got these guesses as to what might happen with the 24th cycle. It's either going to rise slowly or steeply or somewhere in between there. Those predictions depend on who you ask. There's different sort of computer models for these different predictions. So you have different kind of computer models that would project what you would get. And some of the models project, rising slowly, some project rising quickly, and so we have kind of a combined sort of thing. The Belgium physicists seem to believe that the 25th cycle is going to increase in activity a little bit faster than the American scientists do. So we'll see how that all pans out. We're not really sure yet. When you're looking at sunspots, you notice there's kind of a very dark inner portion of the sunspot and then a lighter outer portion. The dark inner portion we call the umbra, and the light outer portion we call the penumbra. And so the umbra is the dark inner portion of the sunspot. That's the part you normally see. Now, why is it dark? Well, it's not really dark. It's the sun itself is blinding bright. So in order to see it, you got to dim the light. If you dim the light so the background part of the sun is not so blinding out here, that makes this part look dark by comparison. It's really still pretty bright. It's just less blinding white bright than the rest of the sun. So the rest of the photosphere. And so it looks dark by comparison. So it's not really that dark. Most sunspots don't occur by themselves. They occur in groups. This is a compound group right here where you see a bunch of umbras in there, and all the penumbras tend to run together. That's often a very common sort of thing from a complex sunspot group. In measuring the sunspots, one of the things that we discovered is that they have a magnetic field. Well, how do you measure the magnetic field of a sunspot? Well, Peter Zeeman, a physicist, realized if you look at the spectral lines of some elements. Now, again, we know about spectral lines from our study of light and spectroscopy. In the presence of a magnetic field, electrons going around one way have a magnetic field of their own, electrons going around the other way a magnetic field of their own, and so that means if you put an external magnetic field in here, going one way has more energy than going the other way. And so that means that these spectral lines will split based on whether the electrons are going one way or the other way. and that would be a slightly different amount of energy. And so remember, the spectral lines you get are from energy transitions if an electron goes from one energy level to the other. And so that gives you the spectral lines. And so if you change the energy slightly, then you have different options right there. So if you were to take a slit right here and have the light from the sunspot going through that slit right there, okay, and you look at it, then where the sunspot is not, then the spectral lines are pure spectral lines. But where the sunspot is most intense, in that umbra there, the spectral lines split. And by measuring the degree of the split, we're able to measure the strength of the magnetic field. Turns out the magnetic fields of sunspots are ginormous. A weak sunspot has a magnetic field stronger than than you can imagine. A weak sunspot has a magnetic field close to the strongest magnetic fields ever produced on Earth. The stronger magnetic field sunspots actually have a magnetic field stronger than we've ever been able to actually produce here on Earth. Outside the Earth's atmosphere, you can measure this much more precisely than you can here on Earth. And so what you do is you try to measure this, and we can make a map of the magnetic fields of the sun, and we call that a magnetogram. And so one of the things you discover is that where the sunspot groups are, then that is where you have more magnetic activity there. And so the sunspot groups are tied into magnetic activity on the sun. Now, that turns out to be key, because it's that magnetic activity that actually really has a huge impact on what's going on here.